Okay. Everyone can hear me okay? Hear me at the back? Yeah? Awesome. Okay, yeah, my name's Stephen Tovey. I'm from the UK, and I'm here today on behalf of Intel to talk to you guys about profiling using PIX. The talk's going to have a couple of different facets to it, so we'll be going into a very small amount about the general optimization process, and then we'll look at how to use the hardware metrics that we have for Intel GPUs, and coupled with that, we'll look at some of the GPU architecture that you have to kind of understand in order to interpret the metrics. So as this Polaroid up here is developing, I guess we will... did it freeze? It looks like it froze. Yay. We're just turning it off and then on again, and then we'll be all set, right? Yeah? Okay. Cheers, guys. Right. Let's see if it works. This is going great. Crashed again, I think. I can't read the... Okay. Let's see if it works. Yes. Come on. Thank you. Thank you. Amazing. Okay. Now that the Polaroid has developed and we are able to kind of zoom in, this is the kind of general flow for doing any kind of profiling optimization. So first of all, we start off with defining our goals. Like, what is it we're trying to actually achieve by optimizing, by making something better? The next step is to understand the substrate which our application is running on, right? Without this, you can't really profile, you can't really understand what the metrics are telling you, you can't really take any kind of meaningful action, right? So understanding the substrate is kind of key as well. Once you've got once you've got a relatively good understanding of the substrate, we can dig into the analysis, right? So we're going to take a look at hardware metrics, counters, which are sort of pertaining to the substrate where the application's running, and we're going to analyze those and hopefully form a diagnosis of the problem. Once we have a diagnosis, we can go ahead and implement a solution to that issue, and then we validate, and then we kind of do the whole thing over and over again until we are happy with where we land. What are the sort of things we optimize? There's several, but these are kind of the three main ones. We have kind of interactivity, which would be something like frame rate, right? Like how fast the application's running, how quickly it's responding to user input. Memory is another key one as well. How much resources it's using, how much RAM, how much VRAM, etc. And increasingly, with the increasing popularity of handheld platforms and so forth, power is becoming a more interesting one as well. But all of these three things here really are in service to expanding the sort of total addressable market of your application, right? If you optimize better for a specific platform or make something faster, you can target more platforms, target more a lower min spec, for example, open up more customers who can interact with your application. Okay, so let's dig into the actual meat of the talk and start messing around with PIX. Intel, like other IHVs, implements parts of PIX for Windows using the plugin mechanism. So we provide bespoke kind of IHV features through this mechanism, which are sort of surfaced within PIX. And we have a really deep sort of collaboration with Microsoft developing PIX, and we've been collaborating closely with them on lots of fronts. But these three are kind of the big three areas that we're currently focused on and doing this sort of collaboration with Microsoft. So we have what we're trying to deliver is a first-class metrics experience. So this is the counters that we're talking about, and that's the main kind of thrust of this talk. So we're looking to sort of stabilize the counters we've got, consolidate them, and then organize these things into a sort of cohesive sort of layout that you can sort of interrogate and execute a kind of decision tree on the counters to kind of profile your application. In-depth shader profiling is something we're really interested in and looking at. We've got a lot of neat features in the XE architecture which support this stuff, and it's one of the things we're sort of working on busily in the background. Likewise, we hear from many developers, many of you in the audience, about the issues you have kind of debugging crashes and hangs and that kind of stuff, and it's an area that we're really, really focused on and we're doing a lot of active work on. There'll be more on this in due course, but I just wanted to sort of mention the sort of areas that we're really engaged on right now. Okay. Yes. This here is PIX, if you haven't seen it before. It's running on our B580 GPU. How many people in the audience use or have used PIX? Okay, this is good. This is really good. Awesome. This is what we like to see. So here, this is kind of the, if you launch the PIX, take a capture, and then you kind of collect the metrics from a plugin, this is what you will see in the forthcoming version of PIX on Intel. So we've completely overhauled all of the swim lanes that we have, tried to provide a much more kind of cohesive experience. We've got our sort of query-based metrics up top here. We've got all of our hardware counters here. And then this stuff is really providing kind of, hopefully, something kind of accessible and somewhere where you can jump into and begin the optimization process. If we zoom into a region here, this part here, look at these counters, we can see a few different things. The top swim lane we've got here, whoops, sorry, I keep pressing the forward when I mean the laser pointer. There we go. The top swim lane we've got here is just a general kind of breakdown of the different units in the GPU and how utilized they are. And you can select one, and you'll get this kind of waveform here, and you can see how busy different things are. This particular one we've selected here is the XVE, so that's the shader cores. That's the thing that's running your shader code. So that one's a key one, right, as an optimization kind of vector. So how do we choose what to profile? It's kind of obvious, right? You want to find something that's representative of your application as a whole, so you need a frame or a couple of frames or a set of frames which are sort of broadly representative. And when you're digging into kind of dispatches or draw calls and stuff like that, you want to find stuff which has a sort of signature that's sort of consistent with your application. And generally, the metric you use to decide if it's worth doing any measurements, any profiling is it taking a chunk of the frame, right? If it's not taking much of the frame, it's probably not the top priority to be optimizing. So let's take a look here. We've got three kind of very broad signatures here, right? We've got something here at the end which is really hammering the XVE, so this is using a lot of the shader core. Up front here, we've got, I guess, the total opposite, right? We're barely touching the XVE here, very, very low utilization. And then this guy in the middle here is kind of very choppy, and there's lots of noise and chaos happening across the different blocks. So we'll try and dig into these a little bit and see what's going on. Let's take a look at this one first. Before we get right into the detail, we're going to go through some of the computational substrate that the application's running on so we can understand what this stuff's telling us. This diagram here is a kind of cartoon of an XE2-based Intel GPU. You can see here that we have kind of the broad symmetry here, and here, right? These are our render slices. And this contains a number of XE cores, which are these guys here. And inside the XE cores, we have a number of XE vector engines or XVEs. And these are the things that are running the code, right? These guys here, and these here, and here, and here. Additional to this stuff, we've obviously got some caches, ray tracing, sundry other fixed function blocks and so forth, which kind of comprise the GPU. And then up in the middle here, we have like the level 3 cache. So that's like the first kind of point in the memory system where everything can kind of see. And then we have a few global blocks like the front end copy engine, the front end of the geometry and so forth. So that's broadly how things are organized. In terms of the XVE, each of these guys here can have, on B580, can have up to 8 threads, right? So if we start looking at this, figuring out the math, right, we've got our render slice, which is this guy. We've got the number of XE cores in a slice. We've got the number of XVEs in an XE core. And then we've got the number of threads in an XVE. At this point, I should say, by thread, that is the Intel terminology for wavefront, or warp, or wave. So when I'm saying thread, that's what it is. It won't get confusing at all, I promise. So if we plug the numbers in here for B580, you can see we got 5 render slices, 4 XE cores in each slice, 8 XVE per XE core, and then each of those can have 8 threads, giving us a total of 1,280 threads. OK, so we go back to our diagram. Now we understand what this is telling us, right? This graph here, wave distribution, XV thread occupancy all, that's telling us the percentage of those 1,280 slots, or whatever the count is for your specific product, are utilized and running code. And we can see here where we've got this very, very, very low XV utilization, almost no threads running at all on the GPU. So let's do a bit of a thought experiment to figure out the implications of this. We'll see. Do we have any threads? No, we can't compute anything. That's obviously a problem. If we have threads, we can compute stuff. So this seems like it's probably a bit of an issue. Why is this happening? If we look above, we've got the thread dispatcher starved. This guy is telling us the unit that is responsible for launching threads onto the XVEs is starved of input. So it's got no input coming from any of the fixed function blocks which want to launch work to package into a thread and kick it off onto the XVEs. This is obviously a problem. So why is this happening? Let's go back to our architecture cartoon and understand a bit more of the detail. This guy here is a cartoon of our fixed function geometry in the XE architecture. We have a sort of global vertex fetch piece up front, which is part of the middle slice of the GPU. And then we have a bus which distributes stuff out. And then each of the slices that we have, those render slices, those 4 symmetrical things, has a fetcher which begins the vertex fetching process. We've got a vertex stage which maps to the vertex shader, kicking vertex shaders, the tessellation stuff, et cetera, et cetera, et cetera, et cetera, all the way down to the rasterizer. A fairly literal implementation of the graphics pipeline. This guy here, as you might expect, is responsible for fetching your indices from your index buffer and your vertices from your vertex buffer as well, and placing them in a area of cache which lives adjacent to the L3, which we'll meet in a bit more detail shortly. This guy here, the VS, this guy is responsible for packaging up vertex work, indices, vertices, etc., and then pushing them over to the XE cores via the thread launching hardware. So this guy here is responsible for that. If we kind of dig a little bit more into the flow here, we can see how this is working. So we've got our vertex fetcher. It's made up of an index assembly and a vertex assembly, again, a fairly close mapping to the kind of graphics pipeline you'd see in the DirectX, for example. And we've got our indices flowing in from the level 2 cache. They get fetched. Vertices get fetched into the vertex assembler. And then what happens after that is we look at kind of passing these vertices down here, and then we are going to check in the vertex cache here if we've seen this vertex recently. Okay? If we've seen the vertex recently, we can just pass a handle back and say, reuse that vertex. It's kind of like the equivalent of a post-transform cache or pre-transform cache that you might have encountered before. If we didn't see that guy, we're going to allocate space in our little memory that we have for the vertices. So we're going to make an allocation for that, and then we're going to fetch that data and poke it into that URB. So what's going to happen is we're going to allocate, check the cache. If it misses, allocate, handle comes back, vertex comes in, and then we're going to poke that stuff into this URB. Later on, when we launch the thread through the thread dispatcher, it's going to come here, and this guy's going to read the vertex data from this little memory, this URB, into here, and then poke it into our thread, ready to consume that, shade it, transform the vertices, etc., etc. OK, so this guy here holds on to a handle to the vertices, and it's going to keep hold of that until the vertex is completely shaded. Then it will release the handle. It can be reused by other vertices. If we go back to our top-level GPU utilization graph here, we've got here we're looking at vertex fetch utilization. We can see it's working pretty hard. So we want to understand what's going on there. If we ping over into the pipeline state view in PIX, this tells us why. It's extremely busy fetching data that it kind of doesn't need, right, for what it's doing. This pass is doing shadow map rendering. Unless you're kind of doing punch through or something like that, alpha test, you generally don't need extraneous stuff, vertices, like UVs, normals, etc. But this application here is reading up a bunch of UVs and so forth, and the vertex fetcher is busy fetching that stuff that it's just going to not use. So kind of a waste of time putting strain on the vertex fetcher. Similarly, if we look at the Clipper utilization, we can see that it's not quite as taxed as the vertex fetcher, but it's pretty strained for this portion of the frame here. And if we go here over to the sort of query-based stats, we can start to tease out what's going on. One thing I like to do here is PIX has this really nice feature where you can build up custom groups of counters and name them and stuff like that. So what I like to do is I have a group which I call pipeline counters, and I select on here like all of the kind of stock D3D ones plus some bespoke ones for the architecture, and I sort of save these as a group. And then what I do is kind of organize these columns here in kind of pipeline order, right? So you want to have a logical flow from the start to the end, so indices, vertices, primitives, samples, etc., all the way to the end. And then what this allowed you to do is kind of traverse this left to right and figure out where something goes missing, or like where we're culling a bunch of stuff, right? Like we can figure out exactly in the pipeline where we're throwing stuff away. If we look at this guy for the raster shadow, zoom in. This guy here is the number of Clipper primitives going in, and this guy here is the number of Clipper primitives coming out. So this one, death by Clipper, right? It's throwing away like massive amounts of the geometry here. So really could use some frustum culling, occlusion culling, all the kind of basic stuff that should be there. I've been optimizing and profiling games for about 20 years, and it's amazing how often I'm still getting titles with like no frustum culling or like weird frustum culling. So the TLDR here, throwing away entire draw calls at this point is probably not the droids you're looking for, right? It's not the thing you want to do. So for shadow rendering, that sort of thing, set up these PIX counters, take a look at them, get them all configured in pipeline order, make it easy for yourself to discover where something's broken, something's not right, etc. Understand where things are getting culled. Don't fetch data you don't need. None of this is rocket science. It's all very, very straightforward. And do better culling earlier. Again, kind of fairly obvious stuff. I think there's some talks on the first day of the conference about some of this stuff, and yeah, definitely recommend checking those out. Okay. Let's take a look over here. This area here, it's dispatches. It looks, it's really aggressively using the XVE in a lot of areas, filling up the GPU with threads. It's good, right? Let's go back and take a look. This was our flow chart from before. We've got some threads, we can compute stuff. That is good, obviously. No threads, we can't compute stuff. What if we take a better look or move to the next level of questioning in this kind of line of reasoning? Are more threads always good? Let's kind of investigate. So here we've got two graphs. It's just this guy here and the one above it, and we've just kind of chopped into them and kind of pasted it here. So we've got our XV thread occupancy there. That's telling us how many of those 1,280 threads are used. And then down here, we've got our XV busy, which is made up of two signals. One is XV active, which is telling you that it's actually executing an instruction. And the other one is XV stalled, which is telling you that there's threads on that thing, but it's stalled. The purple here is stalled, the gray is active, right? So we can see here how those two things line up. So let's do a bit of stats. If we take the Pearson coefficient of this, and we can do it for the XV active, XV occupancy, and XV busy, and XV occupancy. So that's the gray and the total of the gray and the purple. And we can work out, using stats, how correlated those two things are. So if you've got a Pearson of 0, that means you've got no correlation in the data at all. If you have a Pearson of 1, it means you have very, very high correlation. If you look here, XV active, which is this, the gray stuff, incredibly low correlation with the amount of threads on the GPU. So having threads on the GPU is needed and useful, but it's not the be-all and end-all. It's not completely correlated with actually using the XVEs for anything particularly good. In a lot of cases here, I mean, you can look, this one is doing well. These guys are just stalled most of the time, right? So having threads, not just the end of it. So keep in mind like what the goal is of your profiling, and it's not to just have threads on the GPU. Threads are a tool to achieve your actual goal, which is to make your game faster. What is a better proxy for the actual goal that you have is probably something like XV active, right? It's like this, this gray stuff here. It's like how much of the compute are you using? If you think about computing in general, you've got some sort of fundamental things. You've got like ALU power, computational horsepower, and memory, right? Those are the two things you're bringing to bear on your computational problems. You have an input, some form of transform, and then an output. The faster this goes, the more interactivity we achieve. How do we make this faster? There's several ways. We can simplify the algorithm. We can reformulate the algorithm. We can use more resources to compute it faster if they're available, or we can use the resources better. And what we need to find in PIX, which we have with XV active and, say, memory bandwidth, are two kind of metrics which are kind of relatively direct proxies for the kind of final state of what you want to achieve with the transform. Okay, so if we're looking at this thing then, so what's going on here with all this purple, all the stalls, and the white areas where we've got idle time? Let's dig into that. To understand that, we need to understand the computational substrate, which is the XE core. So this is our cartoon of an XE core. Inside, we have a stack of our XVEs. That's 8 of those guys, like we mentioned before on B580. There's a data port, which has a level 1 cache. We've got our thread dispatcher, which kicks our threads off. We've got an instruction cache, and then we've got some sundry other kind of hardware, which the XE core can leverage to do its work. So we have a ray tracing unit, we have a sampler, which is for sampling and filtering textures, and we have the interface to the level 2 cache if we need to go out of the core to fetch stuff. Let's dig in to the next level. So if we go inside an XVE, this is the kind of broad structure of an XVE. So we've got our data port here, which is interacting with our level 1 cache, our ray tracing units, our sampler, et cetera, and instruction cache feeding in here. And then inside the XVE, we've got a thread controller, which is containing those 8 threads, waves, et cetera, inside that guy. And then we've got our register file, which is where all of the sort of transactional storage for our shader execution lives. So this is where you can read and write and keep data in very fast registers. And then we've got a bunch of back-end instruction execution blocks, like the kind of ALUs, if you will, for the different instructions. And on XE, there's 5 of these guys. There's a message unit, a jump unit, there's an ALU 0, ALU 1, and we have our XMX unit, which is for AI-style operations. When XVE active is asserted, it means at least one of these guys is executing instruction on that clock. So the counter is counting the number of times we have got at least one thing going on here. Okay, if we go back here, we can zoom in and take a look at this swim lane, which is called XVE stall reasons. This guy is giving us several signals which tell us when the XVE is not issuing an instruction, why is it not doing that? And there's a bunch of these reasons here listed, and they each have a waveform associated with them. Because it's a little small, I've kind of broken them out here into a table so we can take a look at them and try and understand them, what each one's telling us. There's two broad categories of these things. There are control stalls and there are data stalls. Control stalls are things which affect the ability of the program to flow, so branches, fetching instruction data from the instruction cache, etc., etc. And data stalls are things which affect the XVE's interaction with data, so fetching things from caches, memory, etc., etc. Let's dig into some of the control stalls. First one we'll take a look at is a message dependency. So this one will make the message stall signal assert. So we have our thread controller. It's going to issue a message. A message in XVE parlance is an instruction which needs to talk to a function outside of the core. So this could be a memory fetch, it could be a ray tracing instruction, it could be a texture sample, something of that nature. And we implement these through messages. So the XVE core will send a message out through the data port, it will get routed to the block that's going to service that message, and it will come back. And we have a unit to handle that, which is called the message execution unit. Inside this guy is a FIFO, and if there's a lot of messages in flight waiting to be serviced, it can fill up. Once it's full, you can't put any more in there, right? So you have to wait for that FIFO to drain before you can put some more messages in. So this is the first of our stalls in the control column. Next one, fairly straightforward, instruction fetch stall. If we go back to thinking about our internals of our XVE, we have a bunch of threads inside there. There's 8 of them, as I mentioned before. And each of these guys has an instruction queue in here, which has some local storage for the instructions, but gets filled up from the instruction cache. So as it's running through that code, it's fetching stuff into the instruction cache and fetching stuff into the instruction queues, ready to be executed. If nothing's arrived in here, you can't do anything, right? You're stalling, waiting for instruction data to come in to the core, and you get an instruction fetch stall. Branches. This is kind of the canonical thing you might think of when you think about control stalls and control kind of dependencies and so forth. Again, we have a jump execution unit. When we make a jump from one instruction to another in the shader code, we have to compute where we're going to jump to, and that takes a bit of time. And if we don't know where we're jumping to, this guy can't go and fetch the instructions. It's got to wait for the address to be computed. We're going to get a stall. So that is another reason we might have a control stall. So that's these 3. We understand what the counters are telling us. Let's look at some of the data hazards. And to do that, we need to understand how XVE's instruction set architecture looks. This is some random bit of assembly code. I don't know what it does. It's just kind of made up. Well, it obviously adds numbers and stuff, but yeah, anyway. So this is the address. These are the opcodes. That's the destination register, source registers, and then this stuff we'll get to in due course. Okay. The general instruction syntax we have on XE GPUs looks a bit like this. So we have, the first thing we have is actually the SIMD width that we're going to execute this instruction at. XE has an interesting property where we can actually vary the width of the SIMD of an instruction on a per instruction basis. So we can run a single SIMD width for one instruction, and then on the very next instruction we can go fully wide, and we can vary it on each instruction. So that's here. The next thing we see is the op, so that's telling you it's an addition, it's a subtraction, it's a multiply, it's whatever. Then we have the destination operand, so that's where we're going to poke the data in when that operation is finished. And then we have the source operands. So these are the parameters to that instruction. So if we're going to sum some numbers, whatever, A plus B, A would be there, B would be there. And then at the back here in the curly braces, we have two funky-looking numbers which are important to understand. The first one is the register distance, and the second one is our scoreboard dependency. What are these telling us? These things are telling us the data hazards between instructions in our compiled program. Let's take a look in a bit more detail. If we go back to our little example and we color these into two types of instruction, we'll have in-order instructions, which execute purely in order, and then we have our message instructions and things which go out to the shared functions, which you can think of as executing out of order. So if you send a message out to fetch some data, you do some ray tracing, you send that message out, it's going to come back at some point in the future, it's going to be done out of order relative to things which come after that instruction is executed. So we call those out of order, we call those in order. If we look here, we can start to plot these dependencies as a kind of graph, right? So we can see that R2 is sourced from this destination here. We can see R6 as a source here from this destination. Oops, sorry, that should say R6. My apologies. Oh, no, it does. OK, there we go. And then R8 is source 1, goes up to R8 there. So we can see here. And these guys are all in-order dependencies, and they are encoded in this register distance syntax. Register distance simply tells you the number of in-order instructions previous to the one where you're reading the data where the dependency exists. So if we look at R2, it's got a register distance of 1. Here, 1 instruction up. And that's encoded statically in the instruction encoding. If we look at the next one, R6 here, we're 2 instructions up. Bing, bing, up to there, address 20. If we look at this guy here, R8, it goes up to here. This one's a little more complex. Because register distance is counting in order instructions, it'll actually hop over instructions which are out of order, right? So we're going 1, 2, and back up to here. For out of order, we use a different mechanism, which is the scoreboard mechanism. Again, this is encoded in the instruction directly. And this example's got 2. It's got 1 in each direction. So we've got a read after write and a write after read. Let's do the R6 one first. So here, we've got the destination instruction of 60, which is reading. It's reusing this, right? So this guy is getting used as a parameter to the message. It could be like a UV coordinate, it could have array in it, whatever. And then we're reusing it again, but we have a dependency. The reason we have a dependency is because this is out of order. So when we send this message, we need to be really sure that that payload has gone out with the message before we blast over the top of it with some other stuff, right? So if this is an address or something, and we don't have this dependency, and then we blast over it here, it's going to do crash, do some weird stuff, whatever. Hopefully it'll crash. Or you might get unlucky and it works. The other way around is this way. So this is the destination of the send message. So it's coming back into R10. So if we've traced array or we've sampled a texture, it's going to poke that back into R10, and we're encoding the dependency here back this way. The way we do this is with this stuff here, the scoreboard. So this dollar syntax here, like $0, that's allocating a scoreboard entry. So we're saying this out of order instruction allocates scoreboard entry 0. And then this guy is waiting for scoreboard entry 0's source bit to be set, i.e. all of this stuff is consumed. And this guy is waiting for the destination bit to be set, i.e. we've written the destination. So we can wait on different things, source and destination. That's what the scoreboard is telling us. So if we see a scoreboard stall, that means this. And then there's an ALU stall, which tells us this one. So here we've understood scoreboard ID, and we've understood send write. Okay? Scoreboard ID is a really good one to understand when you're waiting for memory. So if you're doing a load or a sample or something like that, it's going to show up as a scoreboard ID, right? Because that's the way we're waiting for the memory to come back. So that's a really important one. OK. If we go back to our XV architecture, thread controller, GAs, stuff here, right? Let's dig a little deeper into the thread controller. Looks a little, sorry, the GA looks a little like this, right? So this is the block which has our register file in it. It also has our accumulators in it, and then it feeds into these back-end ALUs. So these are our FPUs and our XMX unit as well. So the thread controller makes a selection from the threads, what instruction it's going to run, sends it down to the GA, and then this guy is going to read the data out of this thing and then send it up here, and then these will write back here when they've computed the result. This guy here, the read controller, this is controlling access to this, the GRF. So all of these things come in. This guy has to decide who gets access. This guy up here decides who gets to write back. So when we are calculating the addresses of this thing to read, we know when we're going to write back and where we're going to write back, because we know the latency of these things, and we also know what we want to read. So we have a kind of scheduling problem that's being solved here. So for ALU write, we'll just kind of delay the execution of instructions so we don't retire things on the same clock, and that's called an ALU write stall. And then we have a GRF read stall, which is we've got lots of things all trying to read from this GRF, which has a limited amount of ports to access it and read from it. So we have to kind of serialize those instructions so that we can read the data clock after clock after clock. And that's these two categories of stall. So that's these two. Barriers next. Again, XE core, we've got our thread dispatcher up top here. When we use constructs like group shared memory, so this is your sort of memory that you're sharing between a thread group. If you just have a crude diagram of a thread group here, this is like num threads 881. This is a thread group, and then these would be our hardware threads in here. If we're sharing memory between these things in group shared memory, or as we call it in the XE parlance, shared local memory, we have to have some primitive barrier to make sure that memory is written there and you're reading things at a kind of synchronized point. So this one is kind of the barrier stall, barrier instruction. So when we send a barrier instruction, it goes out to here, actually goes back up here where everything gets managed, and then we'll wait for the threads to get to the right point, and then we'll let the code execute. So that's the barrier stall. Pixels have a specific nuance, which is this pixel scoreboard. So in here, whoops, excuse me. Let's go back one. Yep. We have a scoreboard which is kind of maintaining the order of how pixels should be executed. So if you submit a polygon and then submit another one, you don't want those guys to shade out of order and then to submit their colors out of order, because you'll get kind of incorrect results to what you were expecting. And that's what we do here. So if you see a pixel dependency, that's what that guy is. And then other, that is everything else. Okay, so we know what those are. We can understand all that stuff. So let's look again at this guy here. So we're seeing, if we look here, we've got our XV busy, so the gray is active, the blue is, the purple is stalled, and then down here we've got our stall reasons, right, which line up with this neatly. So we're not seeing very much stalling going on here, right? It's very, very aggressively using the XVs, which is awesome, but we're seeing very much stall. But we also see, like, why have we got so many stalls happening when there's no kind of actual stalling occurring? It's a bit of a mystery, right? The answer is that any one of the threads in this set of 8 is stalling. We're gonna record it in the counters, right? So we've got 8 threads running on this guy. If one of them is, I don't know, fetching instructions, it's going to say, I can't run, I'm fetching instructions, tick the counter up, right? Or I can't run, I'm waiting for a scoreboard dependency, tick the scoreboard counter up. So it just means that one of these guys is waiting for a dependency. So it's actually natural, it's very natural to have some amount of stalling in normal code execution, right? The whole point of having multiple threads is that you can quickly bounce between them and hide the latencies and stalls of the different threads. So it's entirely normal to have some. The cases where it gets more problematic is when you've got stuff like this, right? Where you've got very high stalls actually being recorded, where the XE is not actually issuing something. And then you can go down to here and dig into the why, right? So is it scoreboard ID? Is it whatever it is, right? So again, this goes back to keeping the goal in mind of like what you're actually trying to profile. You're not trying to make that 0. Like it's a nice puzzle to make that 0, but that isn't going to make your game any better. What you're trying to do is make that high, or make memory bandwidth high, and doing useful, sensible stuff. So getting distracted by kind of like, I'm going to complete profiling, right, and make that 0, that's not going to make your game go faster. Okay, and this is my last slide, I promise, and then I guess it's... So, profiling it's a complex business. There's a lot of stuff you have to understand to be effective. And what you really hope for is, this is the performance of the game, right, going up over time. So the more time I invest in profiling, the better the game gets, right, the faster it goes. Sadly, it's not true, right? This is the real kind of state of affairs. So it's more like this kind of S-curve, right, where you invest a bit of time in profiling, you get good results, and then you very quickly enter a kind of diminishing returns kind of process where, like, to get the absolute maximum out of it, you have to completely rewrite everything in like assembly and whatever. Right? And I guess my advice here is like, don't get sucked into this red bit of the curve. Like when you're doing your profiling, get to somewhere sensible and then stop. Right? Don't again go after the diminishing returns portion of the curve. Okay. So to wrap up, these are my sort of takeaways and I guess conclusions. First thing, know that optimization process, know that loop, like analyze, diagnose, implement, et cetera, et cetera. Define the goals that you want to achieve and focus on those, and don't get kind of sidetracked into like minimizing kind of bizarre other counters and stuff like that, right? Understand your tools. That means things like PIX, right? Super useful, amazing tool. It's got a lot of great data. Spend some time with it. But also understand the substrate where your application's running on, right? Your computational substrate. Having a good grasp of that is incredibly important to get anything meaningful out of the tools. The diminishing returns portion of the curve, I'd really strongly recommend keeping that in mind. Like, obviously, aim for the best, aim for 100%, but stop when it gets silly, right? Otherwise, you're just going to burn a whole bunch of time. Might as well optimize something else, get better returns for your time. And the last one there, really, optimize regularly. There's usually, let's optimize at the end or something. That tends not to be the best idea. Like the best thing in my experience is to regularly kind of revisit things and try and keep things, relatively optimized. I actually worked on one project once where the developers went off and made 2 branches. One was the memory optimization branch, and one was the ALU optimization branch. And the plan was to merge these back at some point in the future. And like, you can guess how that went, right? So yeah, that's it really, and that's me. If you have any feedback on PIX, this is the official Microsoft email. You can drop it there. The team love to hear the feedback. If it's Intel specific, you can reach out to us. We'd love to hear from you. And lawyery stuff. And thank you very much.